Let us slowly start with the introduction. So we were already assuming that you know gradient descent and also on the general level what is stochastic gradient descent, and it was already used in the labs. And we also discussed last time, or in the initialization topic, we discussed how the choice of the coordinate system matters for the gradient descent. So we touched that aspect. But there are much more to that. So we will have 2 lectures on this, on different aspects of the optimization, considering our machine learning setups. So what the different aspects of stochastic gradient descent. So today we cover more or less basic stochastic gradient descent, and then there will be one more lecture on the sort of making it more adaptive and towards that direction. Right. And today, okay, so today we talk about things like understanding what kind of convergence is there, what is the stochasticity, how this gradient descent means, what are the learning rate schedules, what we can do, what momentum is doing, and we talk about things like, okay, why or what it is known about its properties in terms of how it helps to find good solutions to machine learning problems, the implicit regularization. Questions on that? So we will start from more general and maybe more advanced setup than the simple case of just a finite training set. So let us assume that we have a data generator, right? And in the one practical setting is that the data generator is you have your finite training set, but of a given size. But in addition to that, you define some sampler. And that sampler is something that, okay, from your finite data set, it draws examples one by one. Maybe, except of this sampler, you could also do like a randomized data augmentation. So you draw a random sample from the data set, and then you do something with it, like distort geometrically or photometrically or something else. Now, what this sampler could be. So if you have something like data set, you have some instances in this data set, 1, 2, 3, 4, 5. Like the most obvious choice is to, okay, define a sampler which just draws this IAD at random. And we had this discussion about IAD in machine learning, that it is everywhere and important. So the basic thing is to really draw this independently at random, any of these samples. But you will see that sometimes you could, okay, so, but imagine that you don't draw it random, so what's then? So how would you do this? You could do it in this maybe sequential round-robin order, and that doesn't break the optimization, you will see. So that will still work. So it is what really would break it in some sense is that if you start drawing differently, but then it is also doing something to your expected loss. So imagine, for example, that okay, so this data point you draw twice more often than the other ones as a result of the sampling scheme. And then it is, so you have these probabilities of drawing these data points, but then on average, it kind of means that you will count the loss for this training point twice more often. So if you look then at the average, at the expected loss, then it will be a different expected loss as opposed to that if you were drawing them in randomly, or even you were just cycling through them sort of deterministically uniformly. So the sampler together with this data defines the expected loss that you're going to optimize. And sometimes these things like that would be undesirable, right? So it would modify the expected loss. Maybe this is not what you wanted, but sometimes it could be helpful if, for instance, this class, okay, so some data sets that are coming from natural world, you have a lot of examples from the internet, maybe people taking pictures of cats, but maybe you don't want so many cats in your training, and then you want maybe like draw the other examples more often, even though they would be repeating examples from other classes. So they would be maybe sampling the kind of changing the proportions, right? Maybe to balance for your data set in balance. So it depends on like what expected target you want to optimize. So this sort of you can adjust for that by tweaking that sampler. And then I mean, in the more general situation, the generator could be even some simulator from which you get things you synthesize that. Maybe it could be like simulating some physics, or it could be simulating the vision, the autonomous driving, or it could be a stream of data, like, you know, people are browsing internet and clicking all the time, and you have just data every day in sufficient quantities, so you don't even need to record it. So it could be kind of also possible setup. Right, so we have this data generator, and this, let's assume that we can estimate, or at least define in a reasonable way, what is the expected loss. So if you have some input points and we have predictor, and we have the desired targets, but so okay, so for finite data set it's clear, right? So we at least for when there is a distribution that we draw these instances at random, it's clear what this is expected loss. It is less clear for these deterministics orders or for infinite data, right? But now maybe let's limit ourselves to that setup when this is clear, when there is the expected loss, and that we want to minimize. And then if that is the target, then so kind of this IID and so on assumptions are affecting this target, but they are not gonna affect very much what is then going with this gradient descent or stochastic gradient descent. So the common gradient descent, it's this. So we take the gradient of this total expectation, if we can. So, but it could be computationally expensive if the data set is very large, or even could be prohibitive if it includes there some random augmentations. It's really hard to compute precisely this expectation, right? Yeah, so then are we up? Then, yeah, I recall one talk by Stephanie Yegalka at some conference, and like half through it was invited talk, so it was quite long. So half through the talk, she got cut off, so some slide got stuck, and it was on, but it was stuck on some old slide. And she would continue talking, describing the plots, and saying, okay, if you believe me, then it is like that, and so on and so on. And actually, if I knew that, I would not have made so many slides for the remainder of the talk. And then it came back and says, okay, now you can check me. I actually did have the slides prepared for that as well. So stochastic gradient descent. So what we're gonna do, we're gonna draw a batch of data from this generator. So here I'm not saying IADs, we just query this data one by one from the sampler attached to the generator and form the maybe a mini batch of M such samples and compute, like, instead of this expectation, we compute the empirical average, right? So the sample mean of this batch data and take that its gradient and use it for the step. And we can interpret it as a like noisy version of the gradient. So suppose we had this expected loss function. In principle, it is possible to define what is its true gradient, right? And suppose it was even possible to compute. And then what we are getting is like, because of this randomized sampling, we are getting an estimate of this gradient, which is maybe some kind of point here around. And it is just because by this procedure that we are taking the gradient of the like sample mean instead of the expectation, it's gonna be unbiased. So if you had some, so if this sample mean is an unbiased estimate of the expectation, then the gradient is unbiased estimate of the true gradient. So it means that on average over all these stochastic mini batches, we're gonna be like getting the right direction in the stochastic gradient. If there was a bias, it would be like systematically we would have a component systematically in the difference. So the average of this stochastic gradients would be not coinciding with the true one. And yeah, because it's the sample average, so the variance reduces as 1 over m with the batch size m. So we have a trade-off. If we take a larger batch, we could make it sort of less stochastic, closer to the gradient, but then it's a trade-off, right? So we could be, so suppose this is our true gradient, and we are somewhere already pretty close to this true gradient in terms of the variance. So we could use twice more computation and reduce this variance twice. But you know, does it worth it, right? Maybe making a step in this GTL direction would be as good as making the step in that direction. After all, it's sort of a gradient descent step is an approximation because we linearize our target function, so it's approximation to the function. It is some kind of approximate guess where in which direction we would minimize the function, at least if we make the step smaller enough, but we are usually making some finite or larger steps. So, you know, okay, a little bit of stochasticity maybe not gonna hurt. And so if this was our starting point, and there's maybe some optimum point somewhere, and let's say like the contour lines of the function maybe would be something like this. Gradient descent would go like orthogonal to this level sets, and if we choose a small enough step size, it would be some smooth trajectory, so this would be gradient descent, right? Now suppose we have the stochastic gradient descent, so in the first step we kind of randomly go somewhere, and in the next step we randomly go somewhere, but more or less in the direction orthogonal to these level sets. So I guess it would also be optimizing the function. And if you increase this stochasticity, so if you reduce the batch size and let's say the training set is large, it would be, yeah, it would be kind of, it could be more stochastic, right? It could be going up and down, and you know, maybe also optimizing on average, because at least what we know is that if the learning step is small enough, then because we have this unbiased property, that on average we will be optimizing the function. So actually, with this small learning rates, it could be still okay. The trajectory could be still weird, but it would be optimizing the function, right? Then then I'd like to talk about two questions. How does it compare with gradient descent in terms of efficiency? So the gradient descent, we need to go through all of the data set to compute it, but it's like the more accurate direction of descent, so we could optimize faster potentially with this. Whereas the stochastic gradient descent, it could be zigzagging, right? So it will take more steps, but it's cheaper to compute one step. So we can talk about this trade-off. And also what to talk about is to discuss, okay, what happens here? Does this actually converge to the optimum solution, or the red one? Is this red one with the very stochastic, is it going to actually to get to the optimal point? And for this, I pick up from some literature from another course of Mark Schmidt, some results about convergence of stochastic gradient descent, and this allows us to talk about these things. So to discuss the convergence of this stochastic gradient descent, then it's not very obvious what does it mean for this thing to converge, because at every time iteration, so at every step, we are picking a mini batch at random, so it will kind of try to jump in some random direction, right? So even if it is already at this point, it will make a jumping out of that point, right? Because it's stochastic. So the convergence there would be understood in the terms of this equation. So this is what the theory developed. So this is like if we are on the straight trajectory and it's kind of jumping, right, like this, then at every such point we could measure the true gradient. This would be this gradient of the loss at theta k. And then this says, okay, take pretty much take the expected gradient or at each point, the true gradient, and then it says, okay, take the minimum over the over the past iterations of this gradient. So if this trajectory somewhere passes through the optimum point, then the gradient at that point of the expected loss would be 0, and then this value would be 0. So it says, okay, best over the past iterations of this true gradient at the stochastic trajectory. So then we could say, yeah, it reached the optimum. So it has found the optimum, or it's a little bit also not clear. So this expectation needs to be also over the trajectory of the stochastic gradient descent, I guess. Yeah, I realized that maybe I forgot something about this, and I'm not fully sure about this. But nonetheless, so suppose this is somehow defined. Now, yeah, you see that reasoning about this convergence, it requires to make some assumptions. So to somehow define what it means, the convergence, and and make some assumptions. So if the function is that we optimize and restrict it, right? If it's some complicated algebraic crazy function, one could build counterexamples that none of the optimization would work for such functions. So we are interested in some good functions. And the best functions are convex, right? But we are interested in something also relevant to machine learning. So you need to kind of look for something that is still nice for optimization, but is still relevant to describe adequately the machine learning setup. And this setting that is listed here, it's more or less relevant in practice. It says the following. So the loss function is bounded from below, so you cannot minimize it indefinitely. That's easy, right? And it says that the gradient is Lipschitz continuous. So that means that the gradient, if you go through different points of the function, so the gradient cannot change abruptly. So it says that if you are at this point 0, then the gradient at some nearby point is within such a cone. So the farther we are from the current point, the larger it could deviate, but its deviation is bounded by the distance from the current point. So this is like Lipschitz continuity on the gradient. So if the gradient is Lipschitz continuous, then the function is also called Lipschitz smooth. And the last requirement is that the stochastic gradient estimate that we are getting has some bounded variance, right? So it's stochastic, right? So it has some scatter, but suppose we have some constant bound on that variance, like uniformly for all the points. And under these conditions, they could prove some convergence results. And now, what is happening with the convergence? So for the gradient descent, if you use a constant learning rate, constant step size, that converges with this rate like 1 over the number of iterations. And I made here like illustrative plot what it looks like. So this is yeah, the red one is like gradient descent 1 over t with the constant learning rate. For the stochastic gradient descent to converge, to really, in this sense, to really go close to the optimum, it's not enough to have a constant learning rate. So the learning rate must decrease over time. So you need steps of like, you know, this typical rule that you need a sequence of steps which approach to 0, the length of the step approach to 0, but yet its sum is divergent. So at any point, wherever at random it went over the iterations, even if this learning rate has been decreased over one of this already, it would be still kind of also still possible to make enough steps of the enough length to get where it needs to. So for that, this sequence of the steps needs to be divergent to kind of from any point to get to any other point. Usually we don't do this in practice, but I mean this is what the convergence gives us. But there is one more interesting result, that what happens with this constant learning rate. The convergence for the constant learning rate, it can be broken down into, okay, and if this learning rate is this like diminishing but slowly, then you have some results that yes, it converges. But the interesting thing is what happens with this constant learning rate. And it factors then the error bound on the how your gradient, how far you are from stationary point, how far you are from reaching the 0 gradient, is bounded like this. So it's 1 over t, like in the full gradient descent, plus something that depends on your step size, on the variance of your gradient estimator, and what's that, on this Lipschitz constant rho. And this is like this last decomposition that's very interesting. It's basically, so the picture for it would be something like this. So you start from some initial point, theta 0, and then suppose this is our theta star, so somehow optimum solution. Then this theoretical result, it could be interpreted as follows. So you are getting, damn it, like the rate 1/t sort of fast convergence, but to within certain kind of ball of radius proportional to this thing. It's a little bit loose because now we are looking in the space of parameters, but yeah. So you have this constant, like, okay, 1/t fast convergence here. And then there is this constant that kind of blocks the convergence from reducing this error further down. And yeah, so here you don't know what it's going to do, but it's kind of going to stay with that ball. So this is like the picture for the stochastic gradient descent with constant learning rate, what the behavior we could expect. And then in terms of comparison to the common gradient descent, this figure here illustrates what happens. So the common gradient descent converges, right, at rate 1/t. But then stochastic gradient is faster per iteration. To make it converge, you need this rule, and then it would kind of be convergent rather slowly. So then the convergence is slow because of the stochasticity. Now the plot is now not in the iterations but in the work, right? So that accounts for a stochastic gradient is actually cheaper to compute. But because the convergence is slower, then it's like this with this alpha over the square root of t rule. But if you use the constant learning rate, is what happens is that you have like this fast 1/n convergence, and then it stalls, right? So it is within this ball. With the constant learning rate, you're not like optimizing it further down. But here in this region, it's much faster than the common gradient descent, right? So, well, okay, these are, I'm not telling you the theorems and the details, so I'm not even, maybe I'm inaccurate in some details of this, but I think it gives you nice picture and nice understanding of what it could be doing. And this was my goal, actually, to just have the intuition what it does in comparison to the gradient descent and what in terms of optimization. Yeah?
What you would do is like take this alpha, like alpha t being alpha for some steps, and then start to decrease it, yeah? Or it's just like feels like non-com.
Yes.
This figure somehow.
Yeah, now this is like illustrative example, and it's just for the purpose to see what are these rates in equations, how they look like in the plot. But the next slide, I'm coming back to this learning rate schedule, so what you can do with this in between this theoretical convergence guarantees and the constant learning rate side. So yeah. Okay, I think we covered this. There are some remarks you can skip. Now to the learning rate schedule. Yes. So one common practice is to do this, then the optimization as follows. So you train with some constant learning rate for some time, epochs, sort of number of times we visited the whole training set. And then you say, okay, I'm gonna decrease it by some factor of 10 maybe, right? And then you train more with this decreased learning rate, and then okay, at some point you decrease it again. So this some folks gave it a nice name, waterfall schedule for the learning rate, because also, so this is the how the learning rate is scheduled, but also the training loss behaves similarly to that. So it has this waterfall effect that, look, now it has, like, in terms of this figure that we had, this like intuitive drawing that we had, it sort of, if it fits, so this experimentally observed behavior, it fits really nicely to that explanation, in the sense that here you have this fast 1/n convergence, or 1/t convergence, and then it kind of gets stalled, right? And then you decrease the learning rate, and that means that for the smaller learning rate, you have like a smaller target ball where it would get stalled, and here you expect sort of again 1/t fast convergence, and it does that, like it falls, actually it falls so sharply that it is quite unexpected phenomena. I'm not sure why, but somehow during these iterates, it looks like it gets stalled, but it's actually doing some good job, and something is still learning. You just don't see it in your expected loss. But then when you decrease the learning rate, it's showing up. And then once again they decrease it here. It's still decrease. So these figures I talk. So this is training loss, and this is the test error dropping, and also in this cascaded fashion. I took from Random paper, which was investigating different optimization algorithms. But this you would see also maybe in the ResNet paper, in many other papers, whenever they use this like waterfall linear rate schedule, then the training loss would behave like this. So it would drop fast at visibly decrease of the linear rate.
I think it makes like a lot of sense with the previous explanation. Like if for step size is basically too large, then we're jumping around, but we're in the general area. Like we can hit the correct point, kinda, and then if we decrease it, then we can finally, like, we're already there, but we can go to the actual like local minima. Kinda.
Yeah, but it does not explain everything, right, about this. So it does not explain really why here there is so sharp improvement in the very few steps if you decrease the linear rate. Yeah, so there is something that is like not captured by these pictures. And then I think the most recent practices, they would always use like a smoother schedule, like this is called cosine schedule. So it is a cosine function stretched over your budget of the training epochs. So if you are going to train for, let's say, what's that, 200 epochs, yeah, so then it would be just cosine rescaled to that. So you kind of continuously decreasing the learning rate. And I don't know, I mean, so here I don't know what are the big studies are showing, but I've tried this in my practice, and here I've comparing here the test accuracy for using this waterfall or the cosine linear rates, and you see the end result is the same. and it's also quite amazing. I mean, so yes, this blue is getting you better results here, but then once you have this jump in this orange one, it gets back to that trajectory. So I really do think so. While it is kind of looking as it is slagging or getting stalled, it is still doing some useful job.
Maybe a suggestion, like what we see in these graphs, this abrupt drop is actually like full epoch or maybe two of training. So there's a lot of updates in one step.
Yeah, that's true.
So
Yeah.
maybe that's why we see there's a big drop.
Yeah, it's epoch-wise. So it.
It's like slowly getting.
Yeah, it is one epoch. Yeah. Of. So the resolution of this plot is one epoch. So it's maybe not as immediate jump on the iteration level, right?
It goes fast. Usually when you watch it, it
Mm.
goes fast, but it's not just.
And yes, then I don't know. I mean, there are many different schedules for these learning rates, but yes, so I have no idea what.
Sometimes people do some warm up that you increase learning rate first, and then there's been like a lot of attempts. Yeah, like if you look into PyTorch schedulers, you will find many different schedulers. I don't know. For me, like this cosine works most of the time. Smooth.
Well, it's definitely better than the waterfall in that when you're looking at the graph for hours, it starts going up sooner. So
yeah, you also don't need to specify when to drop the learning rate and so on.
Yeah, that's a good point. So it is more convenient in practice so that you don't need to specify whether you make these jumps. And it works pretty much the same or sometimes slightly better. So I guess this is now the common practice. Maybe one more thing to say about this is that all these learning rates schedules, they're kind of finite, right? So we are not talking about the learning rate schedule that would allow you the convergence to the optimum. It is making the method to converge because you are decreasing the learning rate much faster. Okay, so if the learning rate becomes 0, then it does not move, so it is kind of convergence. But it is it does not mean that it reaches the optimum of the function. But in practice, this is what works well, and it's also often the case that with these over-parameterized models that you could reach like a zero training error, and in fact you do actually reach the optimum of your loss within this finite schedule. So we could talk later about that. Just yeah, why it is also like important to think of that it is the convergence designed for this finite training budget. You would think maybe there is some trend and that if you continue training, it will still grow, right? If you look at this function, so that you could possibly achieve a better training accuracy if you continue training. If like just looking at the slope of this function, it looks like it could still be possible to improve this. But we cannot do this because we already reached the very fine learning rate. So we cannot like indefinitely keep decreasing the learning rate and expect this to be growing. And if we were not decreasing it, it would be this trend, right? So then it would, at best, it would continue there. And so it's tricky. All right. Yeah, so the next question to discuss, it comes back to the samplers. So how do you sample this data set? And for this question, I'm bringing up some evidence which is maybe from 90s. People tried. No, okay, not so old. Oh, okay, 2009. It's just sort of experimental verification, but before that it was kind of unclear what is going on and what would be the best practice. So they did such experiment. And they compare into 3 options. So one option is draw at random. For every iteration, we just draw one point at random. The second option is, okay, we shuffle this data once, and then we go round robin order. So this is more or less like there is no stochasticity anymore. It's like deterministic ordering through the data, but assuming the data set was shuffled. And this is,
In the
yeah.
first case, we assumed that it wasn't shuffled. Maybe there was some like dependency between samples, or
In the first case, if you draw independently at random, it doesn't matter whether it was shuffled or not. So it's just.
okay.
So in the second case, if you go this round robin, it is then closely related to what is called incremental gradient descent. And that also converges. So if you have a finite sum of some terms, and if you consider them making a gradient descent step for one term at a time, it still converges. It is fine. So it will work. So these two variants, and the third variant was what we are actually doing in practice, so that we like split the training into these epochs, and in each epoch we shuffle the data and then go in some order. Okay, the other way to say it is that at each epoch we are drawing instances from this data at random but without replacement. So if we have already drawn number 2, then for the next step we're not gonna try 2 once again with some chance, but we only choose from the remaining ones. So the first strategy, which was IAD, it would be allowed to do this. It would be drawing with replacement, right? And now these are the results that they got. So that's, let's see. So this is drawing with replacement, the IAD strategy. And it shows the rate 1/t, as maybe theoretically agrees for that kind of model they are training. So the second variant is that having the data set shuffled and then doing the cyclic training, like incremental gradient descent. And you see here from these slope numbers that this is actually already quite faster than drawing IAD samples. So actually this is not stochastic in that sense, so it's like deterministic cycling strategy, but it is training faster. So maybe you don't need the, drawing at things at random. But then this last one is that you reshuffle at every epoch. So you maybe drawing without replacement, and then the training is even still a bit faster. And the main thing is here is maybe the main intuition here why these two other strategies are faster than the IID sampling is that, okay, so they are organized in such a way that they don't have this chance to use this some training example more than once repeatedly during the epoch. So they are organized in the way that, okay, so it is, we're gonna consider all of the training set at every epoch. And we will solve an exercise to see, okay, how long it will take for the IAD strategy for drawing with replacement, how long it will take to consider every example in the expectation. And we will see that it is much lower expected chance. Do I have this here? No. Did you get this point? So that if you draw with replacement, some of these data points we might not be like picking for quite a long time, because at every iteration we are just picking one at random, right? and then the time to see what was in one given training example may be much longer than if we were sampling without replacement. So without replacement, we are guaranteed to see it after we have seen these. So in the worst case, the n iterations. Whereas for this sampling with replacement, it could take longer. So on average, it's like you are not exploiting all of your training data during the training, but you are looking maybe at a random 60% of it. So something like this. Make sense? Okay, and yeah, so this is then. Sorry, this was the other discussion. This was like about the importance weighting. So if you sample non-uniformly.
This one is meant uniformly. You do it uniformly and still you are slow. So in this first case, this would be all uniform. It's not about like weighting.
Okay, we'll discuss this. We will come back to this in the seminar. So we discussed this sampler and the role of this and the effect of this sampler. And yeah, then obviously now the common practice is this, to shuffle at every epoch and then draw without replacement.
So maybe a question to the stochasticity of this last variant, like compared to the second one. You have something to say about it? Okay, the slope is steeper.
Yeah, no, I don't know. Yeah, I was looking at the numbers whether the scales are similar, and they are more or less. But yes, it seems more stochastic. It could be, right? Because we are reshuffling at every epoch.
I can imagine. I'm just like wondering like whether it's good thing or bad thing.
Mm-hmm. Yeah, and this actually says that in practice you can get convergence faster than 1 over n, so you can get like 1 over the t square. Now, so the next question to discuss is related to the momentum and related to the stochasticity of this gradient descent estimate. So from the perspective of the optimization, it is better that we have a more accurate estimate of the gradient, like closer to the true one. Then we would be converging faster, or we could use like a larger learning rate. So from the optimization perspective, it's good to reduce this variance. And because the gradient itself is the batch gradient, its stochasticity is coming from considering the batch average of the loss functions. It's kind of connected to the stochasticity of the loss function as an average over the batch, right? So I start the discussion from this side. So let's look at the loss function. Let's look at the batch mean, and maybe we are optimizing, and okay, it is somehow stochastic, so that with every batch, with every new iteration, we are measuring something that jumps up and down, because this is the, like, yeah, we took a random mini batch. And in terms of the estimating of what is our true loss of true expected loss at this point, we could say that this gives us unbiased estimate. So on average, if we query this random batch, on average over querying this random batch, we would be getting the right expected loss value. So it's unbiased, but it has some high variance, right? So this plot, it's like, okay, so if you want to look at how our optimization performs, we could basically measure with every iteration the loss on the current mini batch, and it is gonna look like this. So it's like very high variance, but unbiased on average. So kind of from this you can guess the trend. You could also consider maybe, okay, so let's verify it. Let's once at every epoch, let's compute the exact total loss over our finite training set. And you can do this, but this is costly, right? So this costs to go through all of the training set. But we could get these points maybe at every epoch. We could compute the exact training loss, and it will be sort of, it should be in the middle of this stochastically jumping curve. Can we do better? I mean, if you want to be more accurate at the current iteration, so how could we estimate what is our current loss function? Maybe you could intuitively see that, okay, we just maybe need to filter this somehow, smooth this stochastic unbiased sin. We could maybe somehow take an average over the time, and then it will give us more accurate estimate of the current training loss. Yes, so we can do this in several ways, but it will introduce some bias. So if we are averaging the values from the past, not from the current iteration, but also from the past, they are not relevant for our current parameter setting. Okay, so they are relevant, but they are slightly off, right? So you will be like mixing the estimates from the past and from the current time. So we can reduce the variance by averaging them, but we will introduce some bias in this estimate. And I'd like to recall like two techniques for doing this estimation. Is that one technique is let's average using all past values. So you take like a flat sum that okay, so we have some loss values like from the mini batches. And what it would do, yeah, that's what I'm thinking about. So maybe like this. So suppose your data is partitioned into fixed mini batches. And then at the current iteration, you kind of train, you measure this. You draw this mini batch and you make a step, and you get the new value for the loss on this mini batch because you have drawn it. To get the full loss, you would need to recompute the losses for all the other mini batches, which you don't want to do because it would cost too much time. So you only have the value, the new value for this one, but you still have the old values for all the others. So you kind of, what you can do is to keep the total sum and keep this all of these individual loss values, and then once you draw this mini batch, you subtract the old loss from this total sum, and then you add the new one, and then you still have like a total sum where this will be the new, but the other ones will be from the past, as long as they were stuck, getting stuck there. Yeah, so you could do this. So this gives you a way of reducing the variance of this loss estimate. But as we said, because it is using the things from the past, there is going to be some bias which looks as a hysteresis in this plot. So because it is averaging over using this past values, so it will be like, okay, lagging behind the true value. Now this is like one technique with this remembering the things, and the other technique is the running average technique. And this running average technique, it works rather as a filter. So you are keeping the like your current estimate of the loss function, of the total loss function, and you are filtering. So there is this update iteration on this current value of the loss function that says, so we will do this. So we will keep the old values, the old value with the coefficient y minus q, and add our current stochastic estimate with the factor q. Right, okay, so why it is called capital L here? Because it's the average over the mini batch. So the average over mini batch is the sort of, if we are not training, if we are not moving, then what will happen is that in the expectation, so in the expectation this will be the true expected loss, and this will be the true expected loss, and then this 1 minus q and q cancel to 1, right? And then if we are training, then we are having a mix of the stochastic current estimate and like the filtered previous values from the past. So we could do this kind of running filter on the loss, and then it will, by this choosing this q value, we could control between the lots of variance and zero bias, or smaller variance and some bias in this estimate. Now if we got it clear with the loss function, now we take the gradient of this. So if you take the gradient of this mini batch, then yeah, okay, so here in this top scene we have plain mini batch gradient descent. If we were considering computing the full exact loss, we would get the full gradient descent, obviously. If we were doing this strategy and we take the gradient of that, we will get the algorithm known as, or called, stochastic average gradient. And it was used in some context, but in the deep learning, that's not really practical, because for this strategy, we would need to remember not only the scalar losses, but we would need to remember the gradients for all of the mini batches. So to apply this strategy. So that doesn't work. And the last one gives us the rule for kind of filtering the past gradients. And this is known as the momentum in the stochastic gradient descent. So what we are going to do in the stochastic gradient with momentum, we're going to measure this stochastic loss at the current point, then kind of filter it, combine it with our past iterates from the preceding points, our like current running estimate of the gradient, and then we're going to make a step in this combined direction. Okay, maybe quickly, what is, we can do like a bit more math and explanation about what this running average is doing. So this specific running average is called exponentially weighted average. Why? Because if we expand this combination through the iterates, it looks like this. So the iteration 1, it is like combination of just some starting point and the q times our current measurement. And if we expand the iteration 2 and so on, we see that like the point that was k steps behind the current step will get the weight with the factor q to the power t minus k, right? So it's if we like expand all of these weights, so if we plot how we are weighting all of the preceding points as a result of reiterating this procedure again and again till the current point, we will see such a plot. It will be like geometrically or exponentially decaying towards the past. And the first point which we start from is getting this factor, which is high in the beginning, but it diminishes as we trail longer. And we can correct for that. So in the beginning we could start, not so it kind of this filtering, it needs some initial point, and this initial point has some factor here for the initial phase, but we can correct for this. So there is a recipe for kind of constructing this sort of exponentially weighted random mean, but without this initial point. Yeah, hopefully. Yeah, yes, yeah. Yeah, so here, this example below, it shows that, okay, with this kind of rule, if you choose different mixing coefficients for the past and the current at different time steps, you could achieve different filters. So this one with the constant filter, and if you choose this mixing coefficient as 1 over t, over the number of iterations, you can verify that you are getting the filter which is a flat average. So actually you can get pretty much anything between the flat average and the exponentially weighted filter. It is an interesting topic if you can get even something better, maybe by using a second order filter. I don't know, maybe worth exploring. Like what we would ideally want to have is the filter that, something like close to flat average over the past iterations and then neglecting the very old ones. I think that would be sort of better filter from the point of view of bias versus variance trade-off. So here by doing this longer tail gives us the better reduction in the variance, right? But it's also by using the stuff from the past, we are getting more biased because, yeah, this for the gradient measured in some points where we have been like before. No, I mean, like here by changing Q, what you are doing is that you have this or that or this law. Sorry, so there is this initial point which I said we could get rid of it by redesigning this Q, making them dependent on the step t, such that it is exponentially decreasing weight, but without this initial thing. And we can, by changing this Q, we could get something different trends between the exponentially decaying and the flat averaging overall of the past iterations. But there is, what I'm saying is that there is always like a long heavy tail to this, getting the things from the old past, maybe with little coefficients. And if you want to have more variance reduction, it is necessarily also like a longer mass spread there. Whereas having such a filter, I think, would give you also better variance reduction, but less bias because you are not using so many things in the past. But it's not possible to implement this as a first order filter, like this combination of the current and the preceding iterate. But it might be possible to do it with, I don't know, using the, like accumulating some two values. So the keeping the state with the two values and doing the second order filter. I don't know.
Possible, but then you again get into problems like where at the like if in audio terms, but like if you want a high pass filter, you can have like a shelf and then a like relatively sharp drop off, but then you will have an attenuation at the drop off point. So just before the drop off, like you will get more weight to the sample. So I think that would be like problematic in that context.
So what you will get, like a attenuation here or there?
A shelf, then it goes down, but right before it goes down, it goes up, and more up than at the end of the.
Ah, like this.
So I think that would be problematic.
Maybe you can
But like
Yeah.
something like that.
Interesting.
yeah, and you can like get better with higher orders. I think like even higher than gets complicated.
I see.
Like, yeah.
And what about this?
Above my head. I don't know that I have more from practice than from theory. Yeah.
Could this I don't know whether it could be good or not. Yeah, but there is some space. I mean, so my message about this would be, yeah, okay, we know this thing is stochastic. We can reduce its variance by average the gradients from the past, and it helps, and it corresponds to this momentum technique. And maybe if you understand this rationale, it would be possible to reduce this variance in other ways also. Now, maybe last picture in this topic is what is the effect of using the gradients from the past. So if you use these gradients from the past, we have this hysteresis, we have the momentum effect. And this will be nicely seen on the, so suppose you are not doing the stochastic gradient descent, we're just doing a gradient descent. So we are not benefiting from reducing the variance by averaging things from the past. We are only getting like mixing in the all directions. So that means we are getting some inertia towards moving into the directions we have been moving in the past. And then it could be useful in also this hysteresis, this momentum for the plane gradient descent. In the situation when the gradient descent, for example, it was zigzagging like this, it was moving orthogonal to the contour lines of the function. So it was zigzagging like this. But if you average these zigzags, it will be then start moving in towards the direction of the optimum. So this could be useful. So it could like give acceleration. But it also could be detrimental, that in the sense that if we have the inertia, that means we will make a larger steps. So we would be overshooting, and then it would be cycling like this because of that inertia. Yeah, so this has this heavy ball interpretation, and then okay, so this heavy ball sometimes it can overcome the plateau and can help you, but it could also like harm you because it would be by the inertia overshooting. Yeah, so this is like the other counterpart of that. So we are reducing the variance, that's good, but we are getting this hysteresis, this momentum effect, which is maybe good or maybe not. Yeah. All right. Now the implicit regularization topic. Or maybe a call for questions on anything previous. No? All right. Yeah, so to discuss about implicit regularization, I think it will be very useful to also have some different view on what the gradient descent is doing, and how it can be like extended a little bit towards gradient descent with respect to other metrics. And this works as follows. So let's just recall how we obtained the gradient descent, or the common gradient descent. So it was the steepest gradient descent. So kind of approximating our function with a linear function and make like finding this direction which gives the steepest decrease to that linear function, and then making step in that direction. And formally, we could capture it as, okay, making the step as solving such a problem called the proximal step problem. So here, I'm plugging in the linear approximation of the function. So I'm saying, okay, we're going to minimize the linear approximation of the function, but we are adding a penalty which is corresponding to the, okay, we don't trust this linear function arbitrarily far away, so we're going to penalize the deviation from the current point by this quadratic penalty. So this is, maybe we will also discuss this. This is related to the, if you want to solve like a trusted region problem. So if you want to just minimize your linear approximation to the function under the constraint that your displacement is limited, so you only trust this approximation is in some ball, and then you're asking, okay, what is the optimal point of the linear approximation on this ball? And then you could, like, okay, if you minimize with that constraint, you could view it as the minimizing with the Lagrange multiplier, optimizing that constraint. So here, or you could view it as a sort of, okay, barrier function corresponding to, I mean, if here we are not solving for this Lagrange multiplier, so we have some constant here, so some fixed multiplier, and then this is sort of a barrier function for deviating from the current point. And yeah, so if you write it in this form, we can kind of solve this optimization problem. If you differentiate in this step size, this part is linear, we get just the derivative of the function, and this part is quadratic, we get the increment itself, and we solve for the step, and it turns out that the step is this, yeah, the common gradient descent. Now, what is the point of what this view gives us? It makes it explicit that here this particular norm is involved in solving this proximal step. So we are kind of choosing this trust region, or choosing this barrier penalty that is related to the distance in the parameter space, which we took to be the Euclidean distance, and we used this two norm in this space for making this step. And then, yeah, we could generalize this, right? So we could solve for the step by saying, okay, we will add a penalty which will be the p norm to the power p. And then what is our step then? And then this will be the steepest in the p norm gradient descent. And this one has like closed expression like this. We can also consider, okay, like keep it a quadratic norm, but keep it quadratic with respect to some positive semi-definite matrix. So we say, okay, this is called Mahalanobis distance. So you have a positive semi-definite matrix, and the norm is defined like this. So it's a like quadratic with that matrix, quadratic form with that matrix, and the square root is the distance, and here we square back the square root. And we can solve for the optimum step in this formulation, and we find out that, okay, the optimal step, we must rescale the gradient by the inverse of this matrix. And actually, so on one hand, you could view it in this picture, that suppose this was the contour lines of this function, this was our current point, and this black circle was this Mahalanobis distance, like a unit ball of the Mahalanobis distance. And if we were able to choose this Mahalanobis distance such that it kind of aligns with the function, then so basically by choosing this Mahalanobis distance differently, we would be skewing the directions. And if it is aligned with the function, it would be going towards the minimum. But we also see that this is equivalent to the effect that we had from the change of the coordinates. So if you change the coordinates by this rule, so if you take the square root of this matrix and move to this space, then this picture would be rescaled to the, the spherical contour lines for both the function and the norm, and we will be in the normal gradient descent but in that space. Okay, so we already knew this, that it changes like that with the coordinates. Now we connected this to the, choose of the metric for the proximal steps. So it could be reinterpreted also like this. Okay, so this proximal steps in is going to be maybe useful for us when discussing adaptive methods and discussing the like optimizing maybe on the constraint set or constraint parameter set. So if you want the parameter to be constrained from 0 to 1, then what do you do that? Then you could choose appropriate distances, appropriate divergences on the space of the parameters constrained to that set, and that it would be some good nice algorithms. But today I am bringing this also from the point of view of the properties of, what are the implicit regularization, and how this implicit regularization depends on the actually norm that you are using for this proximal step. So, kind of the question about the implicit regularization. What we know is that we have like over-parameterized model, and if we are in this classification setting, we know that with sufficiently many neurons, we could optimize to the 0 training error, and we are still getting like better results even if we use more and more hidden units. So that still gives us better. So it's still 0 training error, but it gives still better test errors. There's some examples with MNIST and CFR10. And maybe the question like, okay, why is it happening? So what is helping us to get better results here? And here is the picture. So you have this classification problem to two classes of points. And I give you some decision boundary which achieves the 0 training error. And that would generalize bad. And there is another decision boundary that would actually maybe be expected to generalize much better. And both are achieving the 0 training error. And we know there are many global minima, right, for the given training set. If we can fit with 0 training error, there would be many solutions that the neural network could find, the learning could find. And the question is like, okay, why how is that happening that we are rather lucky and more in this situation than in that situation? So this situation would correspond to this, this bad overfitting, that we are out of control in the number of parameters, and this would correspond to some, maybe instead in the interpolation. So some results towards the direction that actually showing that it is the gradient descent which is helping us to achieve that properties. And I've collected like a couple of results related to this, which are a little bit diverse in the sense of that whether they are considering what kind of loss functions and what kind of problems they are applying to. But if you gather them together, you are getting some kind of intuition of or like pretty good understanding of what it is doing in the linear models, and also some intuition what it will be doing for the neural networks. So what do we know for linear models? And there are maybe two groups of results. And about this, maybe I had the confusion last time. So one group result is related to the losses which look like this. So like the logistic regression loss, which are kind of exponentially decreasing, or even faster than exponentially decreasing. So if you take this, right, the hinge in the support vector machine, or the logistic regression, then we have the following result. So if you consider regularized problems, so if you add a little bit of the p-norm penalty, then there is this result that the optimal solution, the weights, the length of the weight vector could be increasing with if we decrease the regularization, but the direction of the weight vector will correspond to the maximum margin in the p-norm. So that would be like considering regularized problem with that kind of loss, which makes sense. So if you don't regularize, then the optimum solution is going there. If you regularize, something is happening, then this our orientation is good. So then we are like, okay, maximum margin, right? But now, if this regularization is the p-norm, then the maximum margin is also the p-norm maximum margin, appropriately defined. And there is the following result. So if you have, just consider unregularized problem. So you take without this regularization term at all, but you consider gradient descent for that problem. And we've seen that the gradient descent corresponds to this two-norm proximal problem. Then there is the result that it iterates will also converge to the maximum margin. So it behaves, so the fact that in the proximal problem we have this two-norm on the step size, it has the similar effect to having like infinitesimally small regularizer in the loss function. And so it kind of implicitly, out of all of the possible solutions, it is convergent to the solution which is the max margin. So that's one kind of the result. And the other kind of the result is for the loss functions which have a unique root, unique minimum, like the L2 loss. Or, yeah, it doesn't have to be convex, so it could be, this. Or if it is, I mean, it could be something maybe like this, right? But it has to go up. Yeah, so there should be a unique root. And for this type of functions, the result is a little bit different. Then there is no this divergence in the length of the vector. So then there would be always some optimal solution. And the optimal solution, so it says, okay, so the optimal solution will be closest to your initial point in the p-norm. So then this picture applies. So there is some space of optimal solutions. What is our W? We start from some W0. Maybe usually it's taken to be 0, and then the gradient descent. Okay, so you could find any solution here, right? But the gradient descent sort of converges somewhere closer to this, somewhere close to the solution which is the closest to the initial point. So this is our W T W infinity, right? And it's also again in this p-norm, right? So the closest in the p-norm. And this tells us something. So then this is called like interpolation. Unique finite root. So finite means that it is not at the infinity. So there is the minimum. There is a minimum. And I'm not sure about whether this function is required to be.
Does it need to be this minimum at 0 or no? This is maybe the question, yeah? Like if you say root, it means that the minimum is at 0.
Yeah, root maybe in terms of the gradient. So I'm not. Maybe it is not allowed to have any other zero gradient points because this is about gradient descent. This result, right? Yeah, I will need to look up what exactly that. Yeah, so there were these studies for linear models, right? So this was like linear predictor. Here was a linear model with that kind of loss. Here linear model with this kind of loss, and here this nicely in the spin norms. But then there are extensions also to over parameterized nonlinear models and the experimental verification in the neural networks. And the experimental verification in neural networks, it somehow corresponds to this figure. So that if this is our starting point, and then they tried like, okay, running this stochastic gradient descent with different norms. They call it the stochastic mirror descent. And then if you run it with the L1 proximal step, then this is like here the black distribution, so the many weights are 0 and it's more concentrated closer to 0. If you run it with this 2 norm, it's the blue distribution, 3 norm is this distribution, 10 norm is this distribution. So the 10 norm is given like the weights are, all of the weights are more uniform, right? So there is no small weights. Most of the weights are relatively large and similar in value. And if this is the case, then in our neural network, what it means that many weights are similar in value, that you are taking kind of average, maybe slightly uneven average of the inputs, and this corresponds to the kind of interpolating between these inputs. So it's for that reason it's called maybe the interpolation mode. So we do have this effect that we discussed during the regularization lecture, that if we regularize with the L2 norm, then we expect to see like, and with higher norms, we expect to see more even distribution of the weights further away from 0, and with the L1 norm, like closer to 0. And it shows up also if we just don't have any regularization, but do the gradient descent with this norm in the proximal step. And I checked, like in terms of the distances, that this picture is somehow true or makes sense in the experiments, and they check these distributions. And also, like interestingly, they observed that with these higher norms, with this more interpolation, that it was generalizing better by combining the things. Okay, I don't know how this scales, so maybe this is fine for CFAR, but then for maybe ImageNet, you know, you could tune many things. So you could achieve this 94 accuracy by tweaking the network or the batch normalization, or I don't know what. So it's not like this is very insightful explanation, but I don't think that people are using in practice this P10 norm gradient descents. Right, time up. Good. Just maybe have a look offline. There is also the effect of batch size. So if you have smaller batch size, it's more stochastic. So this is says in the toy data, and people have tried on some real NLP task. Training with batch size 1 was getting the best accuracy, and they tried without dropout and with dropout. So with dropout, it was like better accuracy with larger batch size, but still not as good as batch size 1. So this batch size has the effect as the implicit regularization. Okay, yeah, that's all. And then there's 2 more slides if you like to know more about momentum. So there is about this Nesterov momentum and about how much variance reduction we are getting with this exponentially weighted averaging. Questions? Okay, then good. Then thanks and see you next time.